Hello. Hello, Shiva.
Yes, sir.
You're live on YouTube. Okay. You can share your screen. Hello.
Okay, sir. Fine. Yeah.
Yes, sir. You can start the session.
Okay. Yeah. Thank you. Hope I am audible to you all. Yes. Fine.
Yes, yes, yes.
Okay, boss. Fine. Yeah. So yes, good evening, my dear junior scientists over here. Hope everyone are doing good. Yeah. So today we have gathered here for a reason. Yeah, a reason of happiness, and reason that will add or push you to achieve your dreams. Yes, so it's a milestone for our nation. Yes, yesterday we had a successful launch from our equator. Yeah, so I hope everyone have witnessed a beautiful launch. The GSLV Mark II have carrying the beautiful satellite Nisar into the clouds. Yes, okay, fine. So now we are here to just deeply think and discuss about the mission details of the Niger. Yeah. So hope everyone are excited to come with me here. Yes. I just want to see your excitement in the chat box in the live. Yes. I'm waiting for you. Yes. Okay. Fine. Okay. So now without any delay, we'll be running through the session. Okay. So now just let me explain you what is this session about. Okay, so now we are going to discuss about a beautiful launch in which a collaborated satellite, the NISR, NASA ISRO synthetic aperture radar. It was a payload sent by the both countries, India and the US. Yes, so this was launched into the space using the Indian rocket GSLV Mark II. Okay, so now let's go deep into the mission details. Okay, so now let me introduce you the NISR. So what is NISR? NISR is a NASA ISRO synthetic aperture radar. So if we think in detail about the words mentioned there, we know what is NASA and what is ISRO. Yeah. So these are the both space organizations of USA and India. And then after we can see the word synthetic aperture radar. So what does that mean actually? So what does that indicate? So it is basically a satellite. Okay. So what does this satellite do? What is the aperture mentioned there? So aperture is like something related to the camera. Yeah. So aperture is a type of lens which is used in the camera which allows to click beautiful pictures of the earth from the space. Yes. So the radar is the part. Okay. So again, what is radar? Radar is a detector. Yes. It is a radio detecting and ranging. Yes. So then a groundbreaking international collaboration between the two countries, NASA and ISRO, happened by this mission, which is designed to observe Earth's changing land and ice surfaces with unpredict unpredictable detail. Okay. So it is the first satellite mission to collect radar data in two microwave bandwidth regions, that is L band and S band. Yeah, like so. Then after we have the core purpose of the NISR. So what is the core purpose? As we know that we basically send satellites into the space for different applications. Like so, if we count the applications, we have satellites for weather sensing, we have satellites for communication, we have satellites for defense, yes, we have satellites for navigation, and we have satellites for surveillance. In such a way, first time we have planted a satellite for deep observation into the Earth's surface, which will help to detect the natural disasters of the Earth. Yes. So recently we had noticed just 1 to 2 days back a heavy earthquake in the deep oceans. Yes, that might have affected the seashores of different countries. As you might have seen that many people living nearby the seashores have evacuated those regions. Yes. So in such conditions, to help, okay, to warn us or to find the thing, what is going to happen in the field of like natural disasters, we need satellite observation, obviously. Okay, so in such a purpose, our NISR is going to observe in a detailed way how these climate changes are going to affect the natural disasters. Yes, the disasters like the volcanic eruptions, the tsunamis, the earthquakes. Yes, like so many such disasters can be noticed by this satellite, by its observation. And why it is important? It provides vital high resolution data for the global scientific community. And who are the global scientific community here? The different space organizations who particularly research for the space. Yes, and it offers all weather, day and night imaging capability, meaning it can see through clouds and darkness. Yeah, so here comes again the work of the aperture, the camera with a beautiful lens which is having the capabilities, the powerful capabilities which it can watch through the dark clouds and the darkness. Yeah, it can go deep and it can zoom as soon as like it can measure the condition of the iceberg up to 1 centimeter. It can zoom as close as 1 centimeter region in the icebergs. Okay, so which is definitely impossible by any other cameras. And even though looking from the deep heights, yes, and it scans nearly the entire land and ice covered surface of the planet twice every 12 days. That means every 6 days almost it covers the entire land and the ice covered surface of the planet. Yes, so what we are going to notice by this, we are going to observe keenly to the every part, every corner of the earth. Yes, the lands, the ice, the mountains, the deserts, everything will be observed. And the changes in its geography will be leading to the natural disasters. So thus changes will be observed keenly and that will be helpful to warn the civilization as this is a civilian satellite. Yes, we can call it as a civilian satellite. Yes, okay. But you might be thinking, sir, yeah, we have two countries cooperated and contributed for this. So this might be having a cost efficient. But yes, if I say that it is like cost efficient, but even though we have to spend around $1.05 billion for technically manufacturing this mission. Yeah, like so. And how Nazar was built, a collaborative marvel, again comes here. A decade of collaboration. And you know that by 2012, almost it was like, more than 10 years ago, the plan have started where our scientists have a vision that we should have a satellite in space which should keep a deep observation on the geography of the earth by which it can help us to warn the natural disasters. So as a part of that vision, working for around 8 to 10 years, designing, developing, integrating, and using the advanced payloads and systems, they have manufactured a beautiful satellite. Yes, and then provided the L-band radar system and S-band radar system. Yes, so it contribute the large 12-meter, that is equal to 39-foot deployable mesh antenna reflector, the L-band radar system. Okay, and this antenna reflector is like again a detector. Okay, which used to absorb the things and it is used to detect the changes. Yes, and this L-band is the contribution of NASA. And if we come to the ISRO's contribution, obviously, we have developed the S-band radar system, okay, which is responsible for the spacecraft bus. It is not a school bus or, you know, other bus, traveling bus, it's a data bus. Yes, yeah. And apart from that, we have the satellite integration and testing, and then handled the launch using the GSLV Mark II rocket. Yes, so this is a great achievement from ISRO. Because if we look back into 50 years, by 1975, where we just had a dream to keep our satellite into the space, the first satellite. But then we don't have any such technology that to carry that satellite into the space, then we have to depend on other country. Yes, the Soviet Union at that time, we depended on that country to take our satellite, helping from Earth to the space. Yes, that was Cosmos 3. But then now, after the 50 years of revolution in space industry, we had our own beautiful rockets. Yes, clearing the clouds, reaching the space. The GSLV Mark II rocket, okay, which is approximately having the weight capacity of 2.39 tons, carried the Nisar satellite into the space. Yes, so this is our satellite and our achievement. Then, if we talk about the technical instruments, the dual band synthetic aperture radar has a technical instrument of L band and S band too. Okay, so what is synthetic aperture radar here? It is a sophisticated technique that uses radar signals to create extremely high resolution images of Earth. Okay, so it is like our camera. Yes, we all use cameras. Yeah, cameras for different purpose. Even our mobile phone has a camera. Yes, even when we organize some events or parties, there will be a cameraman shooting something. Yes, we all have cameras, and the purpose is to capture something. Yeah, but every camera is having its own resolution. I mean that in your words, you call it as clarity. Yeah, someone having big phones, okay, which cost lakhs, will be having a beautiful quality. Yeah, yes. I hope you are having one such mobile phone which is having a good resolution. Yes. So, like so, there is a camera in our satellite, that is the aperture camera, okay, which captures the images of the Earth. So again, what type of images? The land side and the water side and different geographical structures of the Earth will be captured by this camera. Yes. So this is beautifully done by the satellite, the Nisar. Okay. And the L band from NASA is having a wavelength longer 25 centimeter wavelength. That means it can actually even capture the things, okay, very closely towards the land. Yeah. And the capability, if we talk about the capabilities, it is excellent for penetrating thicker vegetation like dense forest canopies. Okay. Sometimes you might face some technical issues or network glitches when you reach to the clouds, the mountains. Yes, when you go to the hilly areas, sometimes your mobile phone network goes off. That is because the satellites which are navigating your mobile phones are not able to cooperate with your mobile phones because of the region in which you are. Okay, but this satellite is capable of reaching the denser areas too. Okay, like so the dense forests, okay, scanning all the parts of the earth, and it is having a spatial resolution of 3 to 48 meters of the land. Yeah, like so. And the S band radar from ISRO, if you look at the wavelength, which is shorter, but it is like around 10 centimeter wavelength. Okay, and the capability is having like ideal for monitoring soil moisture and surface changes and less affected by the ionosphere disturbances. Okay, so again, we all know that Earth is covered by different layers. I mean, different blankets of atmosphere. Yeah, and each layer is having its own density because each layer is filled with different gases. Okay, So while you capture an image from outer space, yes, the lens should focus through the different layers of the atmosphere to reach to the ground. Okay. So the ionosphere is such type of a layer. You can find denser gases that may change the clarity of the picture, I mean the resolution, because it is a disturbance for the lens. But still, our camera is having such a capability that even it can adjust the disturbances of the ionosphere. Okay, and it is having a good resolution. Okay, and imaging swath. Here you can see the width of the strip of data collected along the orbit track is greater than 240 kilometers. Yeah, so it can cover till a region of 240 kilometers, almost 150 miles. Yeah, and the antenna is a large 39-foot wide, gold-plated wire mesh reflector deployed after the launch. And I hope you all know why it is gold-plated. Yeah, yeah, to make it defendable from the radiations and other effects from the space environment. Yes. So this antenna is the main thing which is used for the communication again. Okay. That is a very high powerful antenna was installed in the Nisar mission. And here we look more into the Nisar's role in fighting climate change. As we have discussed that the main purpose of the satellite is to observe the climate and predict the natural disasters. Yes, so you can see that it is going to monitor the glaciers and ice sheets. Okay, it is going to measure glaciers retreat and ice sheet momentum. As we know that because of the global warming, because of the release of the monochlorocarbons, okay, the glaciers are melting off. Yeah, so the heavy mounted glaciers, they melt and they turn into the oceans, by which the water level increases. Yes, so which also can cause some disasters. So to avoid these things, okay, I mean, to be warned from these things, we need to know what exactly is happening there. So how we can know that? We can't go deep there and we cannot research from the exact area, right? Yes, at least we need to have a photography research. Okay, by observing that, we can at least study about that and we can uh, make the research like what exactly is going to happen and what happened. Okay, how to prevent these causes. Yes, so that can be studied. Yes, and after that, the movement of the glacial lake again, the water coming from the glaciers. Okay, that can also be observed. Okay, especially like the Himalayas, and then assessing deforestation and carbon storage. Okay, so this camera and radar is also used for the deep forests. Yes. So what it is actually focusing into the deep forest is like it is going to aid in mapping deforestation and tracking changes in carbon storage. So basically, we all know that the civilization makes the carbon releases monochlorocarbons. Okay, and the forests are the lungs. Yes, they turn the carbon dioxide into the oxygen almost. Okay, so again, deforestation is particularly a disadvantage for changing the carbon dioxide into the oxygen. So now this satellite is going to have a detailed view of the carbon percentage in the atmosphere and nearby the areas, particular areas. And it is also going to calculate the forests. Okay, how this carbon can be resolved, the issue of the carbon can be resolved. So that can be calculated. So in that purpose, the deforestation and the tracking changes will be Done. Okay. Then after tracking sea level rise, yes, we also have discussed how the sea level rises actually. It is because of the glaciers melting down and turning into the trees, turning into the lakes. And then it will add into the seas that rises the sea level because actually these glaciers look like mountains, but because of the heat, they turn down into water. Okay. And absorbing soil moisture and permafrost. That means they also absorb the soil, the moisture the present in the soil. Okay, and which is crucial for many things like even for the agriculture and for providing vital input to climate models for better understanding and pace and regional effects of global warming. Yes, so it is basically used to avoid certain global warming issues. Okay, so the percentage of the moisture in the soil can be absorbed. Okay, observing, not absorb, observing, seeing, watching. Okay, so that can be done by the satellite. Yes, and we can see the NISER's role in disaster management. Yes, early warning for geohazards, like so the tsunamis, the volcanoes, the landscapes, yeah, and the earthquakes. What it can do is like it can warn the things. And after that, what it can do is like flood mapping response. Yes, it identifies flooded areas even under dense cloud cover, providing crucial real-time data for rescue teams. Okay, like so, recently we have heard in our country, the Madhya Pradesh, Shivapur district, they had floods. The Indian Army was saving the people in evacuating, helping the people in evacuating from the regions. Okay, so to control these situations, okay, even to help them, we need a good data. Okay, we need a good data of the geography and the natural disaster that happened. So how can we get this data? From the satellites again. Okay, so like so, we need flood mapping too. Yeah, so we can absorb the effect from the satellite and then it can be noticed and it can be shared to the organization helping, I mean the rescue teams, and it will be making help to resolve it as soon as possible. Yes, like so. And infrastructure monitoring. So now what is infrastructure monitoring? So again, it is a kind of civilization. It actually measures land subsidence in rapidly growing cities and structural shifts in critical infrastructure like dams, bridges, and roadways. Okay, so that means so it is going to observe how fast the land is converted into the different structures. Yes, so that is also observed. And then after the environmental hazards, like because of different natural things, okay, and man-made things, we can also observe some environment changes. Okay, so that can be absorbed by the satellite. And then we have a open data policy in which all NISA data will be freely available, empowering scientists, researchers, and disaster managers worldwide to make informed decisions. So this is a very good news to everyone. Okay, as NISA is not going to make the data private. Okay, it will be freely available to all the scientists, researchers, and disaster managers worldwide. Okay, so as this mission policy, I mean the aim is to serve people. Yes, is to help people, is to help civilizations from disasters of the earth. Yes, like the natural disasters. So the data, whichever needed, required, will be shared to the needy. Okay, like so. Yeah. So now let's talk about something about the vehicle that it carried the satellite. Yeah. So obviously it's a Indian pride, the GSLV, the Geosynchronous Satellite Launch Vehicle. Okay, it's a Mark II. Yeah. Then this satellite is actually sent, it will be reaching a orbit where it syncs with the Earth's geographical rotation. Yes, it syncs with the Earth's spin. Okay, so it put the satellite in that area. Okay, so it is manufactured by the Indian Space Research Organization, the ISRO, and the launch site is the Satish Dhawan Space Center, Sriharikota, Andhra Pradesh. It's at the Nellore. Yeah, yeah. So it is the area where the equator passes through and the point where the Bay of Bengal meets. Okay. Yeah. So the significance is that it's one of the India's largest operational launch vehicle, primarily used for launching 2 to 2.5 tons class communication satellites into the geosynchronous orbit transfer. Okay. So our satellite is having around 2.39 tons. So this rocket is best suitable for that mission. Okay. And if we see the key specifications, the height of the rocket is around 49.13 meters and the liftoff mass is around 414 tons. I mean 414.75 tons. Yes, but in which the satellite is almost only 2.39 tons. So what all this 440 tons make is of the fuel tanks, the guidance system, yes, the engines and all those you know, combinedly costs around 414 tons. Okay. And the payload capacity, as we know that it is 2500 kg to the geosynchronous transfer. The capacity is this much, but our satellite was around 2340 kgs only. Okay. And for low Earth orbit, it is around 6000 kgs. Okay. It is the specification of the satellite, the launch vehicle. Okay. If we talk about the propulsion system here, it's a three-stage vehicle. Okay. Each stage employs a different type of propellant for optimal performance. Okay. As we know that we use different stages for a rocket launch. The first stage goes for the core motor. It's a solid motor. Okay. Using hydroxyl terminated polybutadiene. Okay. HTPB as the fuel here, the solid propellant that provides the initial powerful thrust required for the liftoff. Okay, so initially, while the liftoff, the HTPB fuel, the solid fuel was used. Okay, then after we can see the strap-on boosters or liquid strap-on boosters. I mean the liquid strap-on motors L40, each powered by a Vikas engine. Okay, they use unsymmetrical dimethyl hydrazine UDMH as fuel and dinitrogen tetroxide N2O4 as oxidizer. Yes, as we know that in the liquid fuel system, we carry the fuel and oxygen separately, but in the solid fuel system, we carry the solid mixed with the oxidizer. Yes, like so, this is the first stage. And if we look at the second stage, we have a single engine, more vacuum optimized Vikas engine. Okay. And the propellants used for that is the same, the hypergolic liquid propellants, UDMH. That is the unsymmetrical dimethyl hydrazine. Okay, that is used. And the dinitrogen tetroxide as the oxidizer is used for the second stage. And if we look into the third stage, the cryogenic, the upper stage, the ultimate stage. Okay, so this engine is really a powerful engine in producing a greater specific impulse for the rocket. It's an indigenously developed engine. Okay, the cryogenic CE 75 engine, 7.5 engine, sorry. Yeah. So the propellants used in this are supercooled liquid hydrogen and a supercooled fuel. I mean, the oxidizer is the liquid oxygen. Okay. The fuel that we use is the liquid hydrogen, and the oxidizer that we use is the liquid oxygen. And I hope you all know what is a cryogenic stage. What is a cryogenic engine? Yeah. So this is a kind of engine. Even the cryogenic, the word itself, it defines that cryo means icy, genic means generated, engine. That means the engine that works in a icy generated atmosphere. Okay, icy cold atmosphere. Okay, so now these fuels are turned into that specific temperatures. Okay, they were cooled down into the specific temperatures, very super cold, to use in that engine. Okay, so the technologies, this stage is technically complex due to extremely low temperature required to maintain the propellants in liquid form. And it provides the final and precise thrust to inject the satellite into the intended orbit. So as this is the final stage, so this is the main stage where the satellite, the main payload, is put into the required orbit. Okay. So if you look into the timeline, the launch date was, it's just yesterday, uh, 3, I mean 30 July 2025, around 5:40 p.m. IST from the Satish Dhawan Space Center. Okay. And the orbital insertion that happens is like the GSLV Mark II successfully placing the Nisar. Okay. And the satellite into its intended orbit within approximately 19 minutes of liftoff. Okay. So it just took around 19 minutes to put off this successful satellite to that orbit. Okay. And we have put into a sun synchronous polar orbit. And then we had a approximately 740 to 747 kilometers above the Earth's surface. So now the satellite is placed in an orbit that is around 740 to 747 kilometers above the Earth's atmosphere. And the orbital period, if you look at the orbital period of the satellite, and that is approximately 97 to 100 minutes. Okay, that allowing it to cover nearly the entire globe. Yes, so one orbit, it will be taking around 97 to 100 minutes. Okay, and post-launch phases, if you look into the post-launch phases, the deployment, the deployment phase, initially 90 days for deploying the spacecraft's components, including the large antenna reflector, and commissioning phase, where the system checks and calibrations. Okay, and then we have science operations phase, where it begins then after continuing for the mission's life. Okay, that means the deployment will be done. The particular instruments or the components will be deployed after 90 days. Okay, the initial 90 days for the initial 90 days. Then after the commissioning will be done by the system checks and the calibrations will be done. Okay, where in the commission space, and then the science operations space where it begins thereafter continuing the mission's life. Okay. Yeah, and the mission duration and data. So the basic line of the mission, if we look, it is a L-band radar. Okay, has minimum 3-year baseline mission life, and the extended operations. If we look, the S-band radar from ISRO, it is designed to operate for 5 years, particularly over specific target areas in India and the Southern Ocean. Okay, the satellite carries enough propellant to potentially continue operations for a couple more years behind the baseline. That means even though we had this estimated baseline, the satellite carried enough propellant potentially in such case that if the technical instruments works for more than the time expected, so the propellant is required. So for that purpose, the propellant is extra carried. Okay, then we can see open data policy that we have already discussed, that the Nisar science data is allowing the researchers all over the world, the scientists all over the world to access it publicly. Okay, this aligns with NASA's long-standing Earth science open data policy. And if you look at the data hosting, the Alaska Satellite Facility, that is Distributed Active Archive Center, okay, DAAC, will host the mission's data and products. So the mission data and products will be hosted by the Alaska Satellite Facility Distributed Active Archive. Okay, yes. So this is all about the mission. Yeah. So I hope you got something new. Yeah. Something fascinating as ISRO day by day aims to put something new in the space. Yeah. Working with the ISRO, you too could be having such a aim. Yes. To put something of you into the space. Yeah. We are born on the earth. That doesn't mean that we are limited to the earth. Yes. Get your wings back. Fly as much as high you can to enter into the space. Yeah, the space is waiting for you. So there are many more opportunities for you ahead. I wish the very best and best of luck for you all to be successful in the space sector. Yeah, then this is all about the mission today. If you are having any such things to discuss more, you can put in the chat box.